I'm David Doughty. I'm the chairman of the History of Hydrology Committee of the Section of Hydrology of the American Geophysical Union. We are lucky to be here in Boulder today at the international meeting of the IUGG and of the International Association of Hydrological Sciences, and thereby to be able to interview some of the prominent people in the past of hydrology. And today we're going to have Steve Burgess interviewing John Phillip, world-renowned in infiltration theory and in soil science. And Steve Burgess from the University of Washington is the one who is going to interview and introduce him. And with that, Steve, would you take over and find out about John and his achievements?
Thank you, Dave. John Phillip earned his Bachelor in Civil Engineering degree in 1946 from Melbourne University in Australia. He earned a higher doctorate, a Doctor of Science in Physics, in 1960 from Melbourne University, which was based on an assessment of his first 19 papers. He's been recognized extensively for his contributions. He received the Horton Award in 1957 with D.A. de Vries from the American Geophysical Union. He's received the Lyell Medal from the Australian Academy of Sciences in 1981. He has received the Horton Medal in 1982 from the American Geophysical Union, and the citation and his reply are published in EOS, The Transactions of AGU, July 27, 1982. He's a Fellow of the Australian Academy of Sciences, and he was elected there in 1967. He's a Fellow of the Royal Society of London and was so elected in 1974. He's a foreign member of the Russian Academy of Agricultural Sciences and was so elected in 1991. In 1995, he was elected as a foreign associate of the U.S. National Academy of Engineering. He's a Fellow of the Royal Meteorological Society, the American Geophysical Union, and the Soil Science Society of America. Now, start off by asking John, we're going to go through in some sense of chronology, but tell us a little bit about your early years and where we lead in and ultimately get to your contributions in science.
Well, Steve, as you know very well, I was born into the lower middle class of Victoria, Australia. And on my father's side, I was, I guess, third generation Scots Australian. On my mother's side, second generation Irish Australian. So there's a lot of Celt there. Do you want me to keep talking?
Yes.
Okay, well, I suppose I would have to come clean and say that my mother was certainly my strongest early influence. She'd really come up the hard way, but after a pretty awful childhood, she finally became a school teacher and indeed in later life became a Methodist lay preacher. How's that? She had an enormous respect for learning, but I'm afraid not the faintest idea what it was. She imbued me with a passion for learning, and I'm still working on finding out what it is, I have to say.
Right.
Now, I guess, am I talking too much?
No, you're doing beautiful.
Okay. I guess I was a precocious child, and I was sort of egged on in this by my terrific mother. The other kids must have really hated me. I think they did. Very often, I seemed to pass through 2 grades in 1 year, and I ended up winning a scholarship to Scotch, which, as you as an old Australian will know, is virtually the greatest public school in Australia.
In Melbourne.
And of course, public school in Australian parlance equals private school in US parlance. And I must have been about the poorest kid at that school, but it really never was a problem. And at that school, I would say that the strongest influence, as far as the long term was concerned, was Stonk Ross. Now, Stonk Ross, believe it or not, was the senior mathematics master at the school. and he was really the black sheep of the school. All too often, he arrived at school hungover, with stale alcoholic breath, and he tended to also disappear to the racecourse now and then, I believe. But this was overlooked because of his passion for mathematics and for excellence, and he somehow could impart this to his students. And I remember one class I was in of 6 in leaving honours maths, and of those 6, 3 went on to be Fellows of the Royal Society of London. The 4th and 5th became professors of physics, and the 6th one went into biophysics and worked with Nobel laureates Schrödinger and Delbruck. So he turned them out. It's time for me to stop. You to tell me what to say next.
Oh, you're doing just fine. John, in the process of doing that, because you jumped through grades fairly quickly, you'd finished high school requirements at about age 13, but too young to start university.
Well, that's right. At that time, the matriculation age at Melbourne University was 16, and I had to mark time for 2 years, essentially.
So that's where you got the opportunity to do the additional honours mathematics and
That's
spend
right.
more time around this interesting character.
Well, that's right, sure.
Not a bad achievement for a class of 6 to have such a distinguished end product. A little bit of commentary perhaps about your sojourn at Melbourne University and your graduation from there and the things that came along from that.
Well, perhaps I don't know whether you can tolerate this, but I don't think I've ever told you this story, Steve, but when I went to the university at age 16, I had not the faintest idea what I wanted to do. And really, left to myself, I would have done law. I'd been sort of, well, uniformly not too bad across the board in whether it was languages or history or mathematics or science. And I had a sort of rather a hankering to do the law. But my Methodist mother saw the law as the path to moral ruin.
Oh, she was very wise.
Well, I don't know about that. But she was quite confident. She also was quite wise about the, shall we say, rather fragile nature of my moral fibre, because she was quite convinced that if I went into law, I'd get up to no good.
Aha.
And on the other hand, in her life in rural communities in Victoria, she'd seen the good works of the civil engineers. They'd made the roads, they'd made the water supply, they'd built the bridges, they'd provided sewage even here and there. And she felt that civil engineering was a noble profession, and in it I would get up to no great moral harm. So, essentially, that is probably the rationale as to why I did my 4-year course of engineering at Melbourne University. But I have to say, looking back, that engineering course was a wonderful way of stultifying creative thought and discouraging curiosity. It would be difficult to invent a more damaging preparation for a research career. The basic message of that engineering school at that time, and heaven knows what's happening now, was this: all things are understood, and all a young engineer needs to do is to know what handbook to use. Over to you.
It's worse now, isn't it, John, in the possibility people use computer software instead of the handbooks?
Well, you said it, I didn't.
Okay, all right, fair enough then. But when we were chatting earlier, you mentioned that perhaps that was not the most exciting curriculum, and you got very good at snooker, billiards, and realizing there are other things than engineering and so on.
Well, you mean drinking beer, and I think I did say incorrectly to you chasing women. It was actually chasing one woman,
right,
who will be referred to later.
Right.
But that did seem to take a lot of time.
I can understand how that would take time.
Yes,
and
yes.
Come the age of 19, you'd completed your course, and let's take it from there. What follows from there?
Well, whatever I was at age 19, I was probably just as miserable a conformist as most of my contemporaries. And so I did what they were doing, and I recall that all of them were at least 3 years older than I was, I guess. And what they were doing was going for jobs in Victorian state government engineering departments. So I did the same thing. And when I fronted up, I was told, "Oh, sir, you are not an adult. If you were, we'd offer you an engineer's salary of £330 a year. But since you're only 19, we can only make you a cadet at £205 a year."
Yeah, we may need a little interpretation here. The pound, shillings and pence system disappeared in 1966 and then became a dollar system, right? But a pound was worth something then.
Well, a pound wasn't worth all that much in US dollars then. It might have been 4 if the Australian pound was being lucky.
Right, okay.
Anyway, I was hungry for money, and my hunger was not going to be met on 205 pounds a year. So, in fact, I began trying to get myself a job as a labourer in the railway yards.
It would have kept you fit, John.
Well, it might have kept me fit, and it would have been more than 205 pounds a year.
Right.
But just as I was sort of taking the plunge into that kind of life, suddenly there came into my awareness an advertisement from Melbourne University seeking a graduate assistant in agricultural engineering, and the salary offered was £350 a year, with no questions asked about age. So, in this way, I got a job in a certain direction by a pure accident. And this was a 12-month job, and for the first 8 months of this, I was sent to the CSIR, as it then was, Irrigation Research Station at Griffith. Do you want an explanation about what CSIR?
Yeah, tell people what CSIR was.
Okay, well, CSIR was at that time the Australian Federal Government Research Organisation, and CSIR stood for Council for Scientific and Industrial Research. A few years later it became CSIRO. They essentially kept the acronym with an O on the end, but it then meant, and we won't have to go through all this again, I trust, the Commonwealth Scientific and Industrial Research Organisation.
Right.
Anyway, I ended up at this place, and I was supposed to be discovering what was going on there in the way of research on the hydraulics of furrow irrigation, and I was supposed to bring the glad tidings back to Melbourne University, and it was hoped that I might be able to lend a hand here or there. Well, now, what I really found there was that there was a team of agricultural scientists who'd been, dare I say it, struggling for a decade to understand the hydraulics of furrow irrigation. And, at least as far as these people were concerned, there actually were things that were not known. And there were people who passionately wanted to understand these things. And this was such a refreshing change from that engineering school.
They needed to know answers.
And so, and what was even better, I found that my own very modest stock of mathematics and physics seemed to start to shed light where no light had been.
Right.
Sort of in the land of the blind, the one-eyed man seemed to get away with it.
Right. Right.
So it was there that I experienced for the very first time the intellectual challenge to unravel phenomena that weren't understood, and the real pleasure of being actually encouraged to do so. I've said enough. Over to you.
So, right, we're doing just fine. So that was a one-year activity, that research assistantship. And
Right.
from there, you moved up to the Irrigation Commission of Queensland.
Mm-hmm.
So this is 1947. And
well, this was 1948 when I went to
when you
Queensland.
finally went up to Queensland, because you
Yeah.
finished your degree in November of 46.
Well, the end of 46.
So all
the
of
job
47.
the job was basically calendar year 47.
Okay. So in going up to Queensland, we're talking about the rebuilding or starting of building of infrastructure for a country that had been completely consumed previously by depression and then World War II activities. So the opening up of irrigation areas was one way to start putting part of the country to work and resettling some
Well,
soldiers.
there had been during the 1930s an effort at irrigation development in Queensland, but possibly largely due to the depression and then subsequent war, it had fallen really rather into desuetude and had really not got off the ground. So they were making a new start with a newly constituted irrigation commission.
Tell us something about the learning process involved and activities involved there in that 3-year period, which was getting your nose rubbed in the dirt, right?
You're a polite sort of gentleman. You call it dirt.
Anyhow, tell us your feelings on that.
Well, I found myself sort of thrown off the deep end into the situation up there, and I was looked on. I was called on to do many things that I think were beyond my competence, but I think I can say without shame they were also beyond the competence of anyone else that was around.
Fair enough.
And I found myself doing everything from designing individual irrigation farms to designing irrigation areas to designing total schemes to doing alleged economic feasibility studies on alternative irrigation schemes and alternative ways of producing dams to serve the schemes, etc., etc., etc. And all of this, a lot of this, of course, was design in a drafting office.
Right.
But there was a goodly part of this when I was actually out in the field, laying out main channels, etc., etc., studying potential methods of irrigating tobacco in North Queensland, etc., etc.
Right.
Designing, in fact, I'd forgotten about that, but also designing irrigation experiment farms that they were setting up.
Right.
So I had an awful lot to do in that actually it was really about 3.8 years that I was there.
Almost 4 years.
A bit short of 4 years,
Right.
yeah.
And you're surveying, you were limited to a 20-second accuracy theodolite with an old metal vernier on the side, and all the hard work, 7-figure logarithm tables for doing the arithmetic, correct?
Well, that's right, but also with an experienced chainman, which was a good idea.
The chainman was the key component.
That's right.
We were legally constituted and authorized to do the surveying in that era, but unfortunately we didn't have the skill that the chainman had, right?
Right.
Fair enough. In that time period there, you and Frances were married in 1949,
Right.
correct, while you were there, and you had first met her in 1939 when you were both aged 12.
Yeah, I guess that's right.
Fair enough. Now, from that experience, John, how did you end up back at Deniliquin in New South Wales?
Well, I guess it was that people in CSIRO, as it then was by 1951, remembered that this odd character had been at Griffith and it seemed to know what he was doing, at least know what he was doing more than some of the other people around did. And I was invited, more or less out of the blue, to take a research position at Deniliquin where they were looking for someone to pursue research on the hydraulics of border irrigation of pastures.
There are many folks who probably couldn't find Deniliquin on a map. Tell them roughly where it is, John.
Well, it's about 40 miles north of the Murray, and the point that you go north from would be north from Melbourne. Do people,
Most people know that
they do know
Melbourne's
where
on,
Melbourne is.
on the-
Okay, well,
yeah,
you
right.
just go due north from Melbourne, you hit the Murray, you go 40 miles further north. It's in New South Wales geographically and politically, but sociologically it's really Victoria.
Okay.
And in those days, the way in which the sociological boundaries were fixed was where the brewery was from whence the beer came. And,
Fair enough.
And Deniliquin was supplied with Melbourne beer.
What brand?
Well, Foster's was one anyway.
Okay, not bad at all. Okay, so the other thing, the Murray River is the dividing boundary between the states of New South Wales and Victoria.
Right.
Little geography there for other people. But on with the activities at Deniliquin. It was not known as an intellectual centre, but there were real issues of irrigation and development and some very fundamental things to be done there.
Well, yes, that's quite true, although you're much more idealistic about these things than I am. But then again, you are an idealist, which I make no claims to be. Of course, I had very strong incentives for getting the hell out of Queensland, because by then I was absolutely fed up with the way in which affairs were managed in a governmental engineering department, and being an egomaniac, I particularly resented the fact that the excellent reports that I was writing and were being published were going out over the names of my boss.
One other thing too, in that work you were doing the complete engineering economic analysis and feasibility analysis for these projects. So you're doing the cash flow series, discounting and trying to figure out what was feasible. So all of that work which you did, other people chose to put their names on those reports.
That's right. Anyway, that was part of it, but of course I had always had at the back of my mind the sort of turning over of the questions that I was asking myself at Griffith and had no opportunities to get on with answers to. And so, in fact, you can gather the extent of the incentives that I had to get the hell out of Queensland by the fact that I dropped 25% in salary, and I inflicted on my poor wife the ordeal of us living in a tent for the best part of a year after we got there, because there was no available housing in Deniliquin at the time.
Right. Now, for somebody who was keen to take £350 a year as opposed to 205, 25% was a significant number, right?
Well, it was, but of course by then, in fact, my salary had gone up meteorically, that's the word,
yeah, big word.
Meteorically in Queensland. I sort of seemed to climb rapidly up the pecking order of the engineers there. But at any rate, so it didn't leave us, the 25% reduction didn't leave us below the breadline.
Right. John, if you'd stayed there a bit longer, you probably would have been able to put your name on the reports.
I don't think that would have been incentive enough.
No, fair enough. Okay, so back to Deniliquin.
Okay. Well, again, I mean, I think you will have seen by now that my career has really been very much a random walk with an awful lot of luck in it. And my luck held good very much very soon after I went to Deniliquin, which was in November '51. And early in 1952, Dr. Otto Frankel, who later became Sir Otto Frankel FRS, became the chief of the Division of Plant Industry, which was the very large division of CSIRO to which the Deniliquin laboratory belonged. And I have to say that whatever I've achieved since my arrival in Deniliquin was due to the enlightened research environment that he provided. He fostered creativity, he cherished high standards, and he encouraged productivity. And I would have to say that if the present management philosophy that I observe in today's CSIRO, and indeed I think this is not confined to CSIRO, but seems a worldwide thing, if that philosophy had prevailed at that time, I should have rapidly become a dull, grey, bored 9-to-5 worker. Maybe I am, but I would be even more so than I am.
Certainly not 9 to 5.
Well, anyway, and I would have been indistinguishable from the dreariest form of bureaucrat. And I really cannot understand how anybody can do any research in the regime that prevails today.
Understand. Tell us a little more about Otto. I understand that he and Popper had some connections.
Oh yes, well that was an interesting sideline in that Otto Frankel and Karl Popper were both children, I don't know whether they knew each other, I expect they didn't, in Vienna at about the same time in the early 1900s. And curiously enough, they both had rather different trajectories, but both of them ended up in Christchurch in New Zealand round about 1938.
Right.
And they were both in Christchurch until, I guess, after World War II had finished, and Frankel indeed until 1952. So, and of course they got to know each other extremely well in Christchurch. Yes.
So the enlightened view of Otto may have been influenced a little by Popper and vice versa.
Well, there might have been some element of that. I believe that Popper is rather out of fashion these days, so I'm not too sure how much I should beat his drum, but still.
I happen to think he had a few good clues myself, but that's okay.
Well, yes, fair enough.
That's we're not in disagreement on that one.
Okay.
There. So out in Deniliquin, you started working and following up on these questions and things you'd observed back in your first year as a research assistant. So now in 1951, going in 52, you're starting to do the polishing work that led to the famous set of 7 papers. John, don't worry. I'm telling you, everybody knows that they're a famous set.
Okay.
So there's something about a little later in there, De Vries comes in there.
Well, let's get ahead of things.
I'm
here.
just giving you a few things to chew on here, right?
Okay. Well, I think the first thing I'd like to return briefly to Otto Frankel. I think there are other aspects than the Popper one which are of interest to me anyway, and that is that when Otto came and visited us at Deniliquin, which was a pretty remote outpost of plant industry, he patiently listened to my account of the adventures I was embarking on in the mathematical physics of the environment. But he was a geneticist, and he had no way of knowing whether I was a snake oil salesman or not.
Right.
And although he might have thought perhaps this guy's all right. But at any rate, he ordered me to come to Canberra to display my wares to 2 professors at the National University, namely John Jager and Pat Moran. Now, a lot of people will know of John Jager as the Jager of Karsler and Jager, conduction of heat in solids, which incidentally you may not know is Oxford University Press's greatest mathematical bestseller of all time. Did you know that?
Well, I didn't know that, but we all have a copy on our shelves.
Okay, and of course hydrologists know Pat Moran for his work on the statistics of dams, etc.
A lot of that was motivated by trying to get reliability estimates for the dams of the Snowy River scheme.
Well, you know more about this than I do.
That's okay, but...
Okay. Anyway, both Jager and Pat Moran received me very kindly, and it seems that they must have reported to Otto that I wasn't a snake oil salesman, because I more or less got the green light to follow my nose, so to speak,
right,
in the work that I was doing. And over the years, I must add, I benefited greatly from the interest and encouragement of both Jager and Moran. It's nice to have people whom you respect believing that what you're doing is worth doing.
Now, a comment about Australian National University. At this stage, early 1950s, this was the dominant research university or advanced study institute in the country, right?
Well, yes, I think that would be true. Basically, at least until the end of World War II, there was no real tradition of research in Australian universities. They were basically on the Scottish model of purely teaching universities.
Right.
And the vacuum, or the gap, had been filled since about 1929 by CSIR,
right,
the government-supported research in CSIR, which was along themes that were important to the national interest. But it was not an agency purely for ad hoc research. It was filling an intellectual gap in the country.
Right.
And the first, well, there were the first stirrings of some research going on in the various state universities after the end of World War II, but it was slow happening. And a great impetus to research in the universities was the setting up of the National University in Canberra, initially purely as an Institute of Advanced Studies.
Right.
And I'm not sure of the chronology, but it really got off the ground, I suppose, by about 1950.
Right, and both Jaeger and Moran held professorial chairs.
Yes, they were really foundation professors. I think Moran was a foundation professor of statistics and Jaeger of geophysics.
Right. Okay, John. So they obviously said, this chap's okay, Otto, turn him loose, okay?
I think that must have been what happened, yeah.
You never quite found out, but that's presumably based on everything else.
My natural delicacy would
yeah, right.
credit that.
Right. Okay, so we're 51, 52. Tell us some of the things going on then.
Well, can I put it this way? I think I've already mentioned this to some extent, that my stay at Griffith had opened my eyes to the huge scope there was for applying physics and mathematics to flow and transport processes in the natural environment. And now I found myself at Deniliquin with the opportunity and the freedom to follow through on this. And, you know, quite honestly, I suppose I've been trying to do this more or less ever since. Do you want to talk about the theory of infiltration series and get that out of the way? It hangs heavy on me.
I think it's quite appropriate because there are quite a few elements here that very few people know about. And I think they'd enjoy hearing about it.
Okay, well, let's have a go at it.
Right.
Ever since I'd worked on furrow irrigation at Griffith in '47, I'd been pondering the question of how to quantitatively analyse the physics of infiltration, of how water actually soaked into soil, which seems a very simple thing, but it was a great mystery at the time. Sometime toward the end of 1952 in Deniliquin, I finally saw the light. I read a paper by Arnold Clute, which was based on his PhD thesis at Cornell, in which he'd given a first solution of the horizontal one-dimensional unsaturated flow equation.
Now that was in Journal of...
That was in Soil Science.
Okay.
It was and that really sort of led to my publishing these papers in Soil Science, in that seemed the natural sequel.
Right.
There probably were other ways to go. But at any rate, I saw in a flash the way to go so far as the real problem, which is the much more difficult one of the equation for vertical flow with gravity superposed on capillarity. Now, as you know very well, but perhaps some patient viewer may not, the equation involved is a horribly nonlinear Fokker-Planck or convection diffusion equation. And it's a partial differential equation a little bit like, well, it's like the heat conduction equation, but with some very nasty complications added. Now, at the time, at that very time, I wouldn't have known a partial differential equation if I'd fallen over one.
So you had to teach yourself something about them.
Of course. But I determined to keep on until I'd found the solutions of this horrible equation that were relevant to the physics of infiltration. And I had great faith that they would be relevant, and indeed it turned out that they were. So, early in 1953, I was down in Melbourne doing one of the veriest early computer courses in Australia on the use of CIRAC.
A question, why were you down doing the course?
Well...
You've been out at Deniliquin, you're working on a problem, and you decide to...
Well, the point was that the popular view was, oh, you poor chap, you won't get anywhere with this equation unless you put it on a computer.
Aha.
Anyway, so I became one of the very earliest students of the computer, which some people will find hard to stomach, but there it is.
They should get used to it.
Well, anyway, for its time, this was a high-speed computer. Nowadays, I think a pocket calculator would do rather better. But at any rate, CSIRO had invented this, and it was installed at Melbourne University. So I did the course, which was on programming in machine language. Now, that's something which I expect is quite unknown to the young these days. It may be unknown to you, I don't know.
No. I did assembler code. I'm very much aware of those zeros and ones.
Okay, very good. Very good. Anyway, I did all this, and I think did it fairly well. And what I did find out, however, was that if I was really going to put my wretched problem on this machine, I would have to stand in line for a minimum of 2 years before I could get used to the computer. Secondly, in any case, its memory storage was so pathetically inadequate that there was absolutely no way that I'd have got anywhere if I had put it on it.
Right.
So, once again, I was very, very lucky. This was a great piece of luck, because of it, instead of surrendering my problem to the tender mercies of the computer, I was actually forced to sit down on my bottom and use my brain.
And figure out how to do it.
Exactly. And so I tried to do that. And I had the great good luck to stumble on a number of sneaky but successful little tricks which allowed me to solve the problem in two complementary ways, which overlapped very successfully. Firstly, a series solution which was rapidly convergent for all except extremely large times, which gave the solution in increasing powers of time to the power of half. And secondly, a travelling wave solution which showed that at large times the solution settled down to a moisture profile of constant wave shape moving down into the soil at a constant velocity. So that was rather good, I thought. But not only did these solutions give me answers, but you see at the same time they were telling us the complete mathematical and physical structure of the problem, regardless of the particular accidents of any particular soil. And it told me, for example, that capillarity was dominant over gravity at small times, but that the gravitational effect increasingly came into play as time went by. So, anyway, that's the story of solving the equation. But it doesn't, there's a long story yet to when these wretched papers are finally out.
Let's have the story.
Okay, well, I'd got the first solutions by, I think it must have been about September 1953, and I gave a talk on them at the ANZAS conference in Canberra. How do I translate ANZAS? Triple cubed AS, is it what? The American Association of Advancement of Science? That would
something
be
similar to it, but this is the combination of Australia and New Zealand, right?
That's right. New Zealand is in it as well, but at any rate. You get the thing, the kind of thing it was.
Right.
There was an ANZAS conference in Canberra in January '54, and that talk was published in the Journal of the Institution of Engineers Australia later in '54. Now, that paper gave only a very small sample of results in a preliminary way. It sort of said, oh, look what I've done.
Right.
But it didn't, you know, inflict in excruciating detail the goodies on people. And it still remained for me, in fact, to work out many of the ramifications of the solutions, such as the effects of the initial moisture content, the effect of ponded depth, the effect of the shape of the diffusivity and conductivity functions, and so on the effect of those shapes on the shape of the moisture profile, for example. And then, of course, there was the alarming task of writing up the whole story in a coherent way. And of course I hadn't had the practice in writing papers then that I seem to have had since.
Right.
So I was trying to get on with this in the first half of '54 when I was interrupted at very short notice. At that stage, the whole business of overseas travel by people in CSIRO was a matter of quotas, and when a quota position fell vacant, a great deal of fancy footwork was needed to fill it rapidly, etc., etc. And so I think it must have been due to the good offices of Otto Frankel, I was suddenly ordered to go overseas for a year, and of that year I spent 6 months in the US, and the balance was based in E.C. Charles's soil physics unit at Cambridge University in England, with a few side trips to various labs in continental Europe. One little sideline on the 6 weeks in US was that at the time there was a big problem about US dollar expenditures from Australia. There always is, but it really was bad at that stage.
Right.
And CSIRO people were allowed only $20 a day, and I was only given a ration for 3 weeks stay in the States. And I said, well, I'm a simple sort of chap and I live simply. I think I can live in the US for $10 a day. And so I stayed for 6 weeks. They said, all right, well, if you're mad enough to do that, you can do it.
Right.
So that's what happened.
So you spent some time at which places?
Oh, well now, I guess I landed the West Coast. I think I probably would have first visited Davis.
Right.
And Veermeyer's Department of Irrigation there, I guess, with people there such as James Luthen at that stage. And then I was in Berkeley with Bodman's group, and also with Paul Day there.
Mm-hmm.
And I think at that time Bob Miller would have still been there at Berkeley.
Okay.
And after that, things get a little bit complicated, because I visited various petroleum engineering labs in Texas and Oklahoma, and also I think out of Pittsburgh I visited places like Gulf, and had the privilege of having lunch with the famous Morris Muscat, etc.
Right.
Don't know that you knew that particular encounter before. And then I think I guess I would have also visited Cornell, and I visited Arnold Clute at who had by then gone to Champaign-Urbana,
Right.
I guess.
Right.
Straight after he'd taken out his PhD. And I also did a bit of an adventure into Canada and visited a few soil physics and also porous medium people in building research in Canada.
Right. So you covered a fair bit of ground in a very short period of time.
Actually, I'm certainly not as fast on my feet now as I was then.
Fair
or
enough.
I'm considerably lazier anyway.
Whatever. You've seen the scene. But the main push of that stay was, or that main push of that year, was the 6 month stay in Cambridge.
Yes. Now, I think what I would have to say is that I found that Charles's way of Charles's belief in the fact that problems should be attacked in as fundamental a way as one can, rather than in as superficial a way as one can, sort of rang good bells with me, and I was grateful, if you like, for the reinforcement of my own views of how things should go that I received from Ernest Charles. Now, Ernest Charles was an original thinker who really was the greatest soil physicist who's ever come out of England. But he made the terrible mistake, unlike so many of us who don't make that mistake, of not suffering fools gladly. And a result was that various English fools ensured that he didn't get the credit that was his due. He was never, for example, elected to the Royal Society of London, and that, in my opinion, was a gross injustice.
Right.
And so I would like to read into the record my great respect for Ernest Charles.
And how he was shortchanged.
Well, I don't know how much you can make of that,
No,
but still.
fair enough, okay.
Yes.
Okay, John. So back from that, back to Deniliquin, right?
I'm going to steal some of your water.
You're more than welcome to have some of that.
Because I run dry, I talk too much.
Well, you're doing the talking. We have you on tape. What can we say? Yeah. So.
Well, speak, please.
Oh, well, what can we do? So, back from the trip to England, boat or plane at that stage?
Well, actually, the trip to US and across to England were by plane, but in fact the plane was then a great adventure across the Pacific, in that you would sort of fly all day in what I suppose must have been a Constellation or something, and eventually after a day's effort, and you'd stopped in Fiji and you'd stopped on Canton Island, you finally gratefully made Hawaii, and then everybody heaved a sigh of relief and went to bed in a hotel and had a good night's sleep.
Right.
And then the struggle to proceed went on next day, and finally we made landfall at San Francisco at the end of the second day of big effort.
And back to a hotel and a good night's sleep.
Well,
or some sleep, anyhow.
Some sleep, anyway. But, and then, well, at any rate, that was by plane. In fact, my family joined me. They went over to England by ship, and we all went home by ship together.
Right.
And that, of course, was a 5-week exercise in those days.
Did you go through the Suez Canal on that one?
Yes,
okay.
Indeed. Yes.
All right.
Yes.
So now back in Deniliquin.
Right. So I didn't get back to Deniliquin to the task of completing the subsidiary calculations and writing up till about July of '55. And I'm not really sure of precise dates, but I think it must have been about January '56 that I started submitting the series to Soil Science. Now, I'd originally planned the series as I think 4 parts. Might have been 3, but I think it was 4 parts.
Right.
And so it went off to the journal as 4 parts, we'll say. And reviewing seemed to take forever. It seems to still do that now and then, but at any rate, it did
We
seem to
won't
take
pick
forever.
on any particular journals.
No, although we might. And it must have been early '57 before the reactions came back. And the main reaction was, oh, these parts are too big, there's too much in them. And I was ordered to break it up into smaller bits. And that's the history of why the thing finally appeared as 7 parts.
Right. Now, today someone would ask you to take 7 and make them into 2 or 3 or something, right?
Well, I don't know.
Right.
But at any rate, I would have to say that I'm not really averse to the notion of smaller parts. I know some people complain, oh, that sod of a Philip, 7 parts, what a big fuss. But the basic thing is that I think that when you have pieces which are coherent in their own right, it's not a bad idea not to exceed the attention span of your reader and to
Right.
give him a bit that he can chew and digest rather than go on and on and on endlessly.
In that year, in 1957, 5 of the papers were published, and the other 2 were published in '58. But in 1957, you had 16 formal publications, if memory serves me right.
Well, there was more going on than infiltration. And am I supposed to say a little bit about the other topics?
Yeah.
Okay.
If you want to now, or a
well, I
little
mean,
later.
firstly, there was a great flood of things then because there'd been a sort of backlog, really, of stuff that had been happening since 1952, and I guess the log jam finally got broken, and so that accounted for what seemed to be a busy '57, but really was part of a busy perhaps 3 years before that. But how to put this? Infiltration has been a recurrent theme of my subsequent work, and I guess the work of environmental mechanics. But there were also 2 other major themes of my personal work and also of environmental mechanics that really had their beginnings in Deniliquin. Now, in describing these, if I may, I have to bring in the name of Daniel de Vries, a very good friend of mine who returned to the Netherlands unhappily, in my opinion, unhappily for me, after he'd been in Deniliquin for 3 years, to become a professor of physics at the newly set up Eindhoven Technological University then, and he was a very distinguished physicist in the Netherlands until his retirement, and the Queen of the Netherlands made him a knight, and all sorts of good things happened to him.
Good.
Anyway, he came as a physicist from the Agricultural University at Wageningen in the Netherlands to work with us in Deniliquin. And the work on soil water movement under temperature gradients, which was very much a work of equal collaboration between him and me, would never have happened without his very important contributions. His presence really got me pondering on the problems of water movement under temperature gradients. And the other very important theme, which has continued in the work of environmental mechanics right up till now, was the problem of local advection, the problem of heterogeneous boundary conditions at the Earth's surface, spatially variable boundary conditions at the Earth's surface, and what these meant for transport processes in the lower atmosphere of things like sensible heat, water vapour or latent heat, call it with what you will, and also for that matter momentum. And he saw that in irrigated areas such as Deniliquin, there were really violent, abrupt spatial changes at the Earth's surface between situations such as water being readily available in excess and often not available at all in other places. And under these conditions, classical one-dimensional, vertical one-dimensional micrometeorology becomes meaningless.
Right.
And we have to develop 2- and 3-dimensional modes of analysing heat and moisture transport near the ground. And so I owe to Dan my early work on local advection and the later work with Norman Ryder, who was an English meteorologist who worked with us for 3 years, and with Frank Bradley, who's an ongoing colleague at Environmental Mechanics, for all the work we've done on 2- and 3-dimensional micrometeorology had its origins in our time in Deniliquin and really, primarily, in the first instance, in Dan de Vries's perceptions.
Right.
And I might add at this point that I've been very pleased to be able lately to build on some of my early work on local advection to provide solutions to the problems of blending heights. Now, these arise in connection with regional parameterization problems which are of great concern to people who are involved in global and large-scale modelling.
Right, right.
Now, another line of work which began at Deniliquin and which has been a major theme of environmental mechanics ever since is what perhaps too grandly we call the soil plant atmosphere thermodynamic continuum. And our perceptions of this arose from our concerns with energies and water balances of vegetation around Deniliquin. And I must say that my early formulation of the total picture was very much stimulated by an article by L.A. Richards and C.H. Wadley from the US Salinity Lab at Riverside. And that came out in 1952, and I think I must have read it very soon after it came out.
Right.
Well, I just wanted to emphasise those broad themes which had stemmed from Deniliquin.
A rough comment on the topography around the area, the irrigated area around there.
Very flat.
Extremely flat.
Right.
Okay, so you've got a lot of variation.
Right. I think the rather bendy or L-shaped main street of Deniliquin was 1.5 miles long, and there was 6 inches difference in elevation between one end and the other.
Ah, very neat problem for storm drainage design. Right. John, after the activity at Deniliquin, there came the move to Canberra, and what gave rise to that, or how did that come about? What divisions were forming? What were the reasons for moving from Deniliquin?
Well, I really don't know what really precipitated the first discussion of the move. I think it may have been that Priestley, who was the chief of the Division of Meteorological Physics, felt that our lines of work was something that would perhaps be fruitfully absorbed into his division at Aspendale in the outer suburbs of Melbourne.
Mm-hmm.
And Frankel, on the other hand, presumably felt rather possessive about this group that he had brought into being. And so to some extent there might have been a struggle between king emperors going on, but I was not privy to this in great detail.
Anyhow.
But at any rate, thrown into this was the perfectly correct observation that the group at Deniliquin, it was all right as a place for them to live while their kids were very small, and educational considerations were not necessarily a major thing. But the time was going to come when there would be discontent about that side of things.
Right.
The other thing was that it apparently was apparent both to Priestley and to Frankel that here was, if you like, a little dynamo generating goodies which really should be having an influence in a scientific environment rather larger than this small accidental one at Deniliquin. And so I surmise that it was thought that it would be a good thing to get these strange people into Canberra, for example, where they would interact with a whole load of biologists and ecologists and whatever.
One comment you made in your Horton Medal acceptance speech in 1982 was the finding of the intellectual base of hydrology in the early transactions of American Geophysical Union. So even though you're out in a small country town and irrigation district, at least you had access to certain library materials.
Well, yes. Well, that of course was one of the very good things about Deniliquin, in that we had a very good, efficient lady librarian there by name Marion Johnson, who was very helpful in getting materials. We had quite a well-stocked library, but the whole business of sort of inputs in hydrology, and especially the early publications of the American Geophysical Union in hydrology, I had learnt to know and love at Griffith way back in 1947.
Got into that there too.
And you see, it is no terrific accident that I became a member of the American Geophysical Union in 1951.
Right.
Before you were born, my son.
No, I was born in 1944, John.
Oh, well,
okay.
you're a seven-year-old whippersnapper.
I was not reading the literature of that kind, the comics, yes, but fair enough. But the issue in there, do you remember what the first paper was in the transactions of the AGU in hydrology, and who wrote it?
No, I have no idea.
By Promptu and Robert Horton, didn't he say something about the scientific directions? You don't remember that one?
No.
We might come back to that a little bit later there, but that's fine. So the move to Canberra, this Otto was putting together a different structure, the agricultural physics section of CSIRO.
Well, of course, we'd rejoiced in the title of being the agricultural physics section for some years at Deniliquin, but Otto decided that this should be moved to Canberra. There was some argument at higher levels in CSIRO as to whether instead we should go to Melbourne. In the end, Otto won the battle and we moved to Canberra.
Which is the national capital. And the reason it's the place it is, it's sort of partway between Sydney and Melbourne because of jealousies between the two capital cities, right?
Well, I suppose you could say that.
That's the polite way of putting it, right?
Okay.
Fair enough. Okay, John. So in Canberra now, the group started to grow, and the housing of the group and so on, and you now started to lead this group.
Well, I suppose I had been leading it, but that's another matter. But the thing is that the original move to Canberra was not accompanied by a very helpful provision of accommodation there. So we were in all sorts of ad hoc accommodations, such as spare rooms in the basement of one building, or a occupation of a temporary building somewhere else, or the occupation of the offices of people who were away on sabbaticals, and all sorts of ad hoc things, which was not terribly good. And this was really the situation in about 1964, when things were getting pretty bad, when an opportunity came to bring our various people together under the one roof in, if you like, a kind of purpose-designed building. And this arose because CSIRO had had a windfall. A rather wealthy grazier had presented one of his sheep stations to CSIRO, presumably as a sort of tax swindle of some sort. And
generosity is the term.
Generosity is the term. But at any rate, CSIRO, the executive of CSIRO, had not the faintest idea what to do with this, but one thing they were sure they weren't going to do was to operate this sheep station continuously as a CSIRO entity. So they cold-bloodedly sold it and then looked around for what they were going to do with the money. And they're talking about a sum of, I guess it must have been something like £500,000.
Which was a lot of money then.
Which was a lot of money then. Anyway, at Canberra, in the Division of Plant Industry, there was the big enterprise there at the time was the construction of a big constant environment laboratory facility for the growing of plants, and this was called CERES, Controlled Environment Research Facility, or something like this.
Right.
It was the acronym for CERES, the goddess of agriculture. But at any rate, I made a great point of the fact that they could spend huge resources on this thing and continue to put a lot of effort and work and research into this. But unless they knew how to relate the environments in this allegedly controlled environment to the real world field environment situation, they had a horrible, embarrassing gap between their labours and the real world.
Right.
And so I put forward the viewpoint that our group really constituted a field environment research group, and that we were precisely the people, if we were properly housed and equipped, who would fill the gap. And this was sort of, I think, one of the important elements in the argument which led to us getting, regrettably not all the money, but some of the money from the Pi windfall
estate. So this led to the formation of the name of the lab is?
The FC Pi Field Environment Laboratory is still over the portals.
And there's something very special about the architecture of this building. Anybody who's visited the Pi Lab, look at it and sort of say, right, there's a place where people can do their work, there's a place where the heavy lab stuff is done, there's a place for meetings and interactions, and there's open space. You have a sense of freedom and space in there. Tell us a little bit about how that architecture came to be, given that normally public works architects would do it, public works builders would build it, and you'd have a stultifying, wretched, typical government building.
Well, I don't know. It's a long story, and probably we shouldn't monopolise this.
We'll have the short version.
Okay, well, the short version really is, firstly, I had a big battle to convince the authorities that this was private money, and therefore there was no statutory requirement to go to government architects and to have the thing done by the government construction department. With that battle won, in the end, and it took a while, then we had to get on with it, and it seemed to me that we had this fixed sum of money, which was only $125 £100,000, as it happened, and we had to get the maximum that we could for that amount of money. And it seemed to me that the efficient way to do this, the economical way to do this, was to see the building as a sort of three-layer cake, with a basement with rough physical space, where things like workshops, wind tunnels, soil storage, all sorts of mucky things could go on, with a second layer of highly developed laboratory space, with highly serviced, and that would be the greatest, that would be the space with the greatest unit cost involved, and then a top floor, a top layer, which would be thinking box space for individual scientists, individual offices for scientists, plus the bit for administration, plus coffee rooms and seminar rooms and so forth. And so then the next thing to do was to sit down and work out what sort of areas fitted. And it seemed that we needed more rough physical space than we did of the others. The others came out about equal, and so it was possible to get rid of all corridors by simply having an open courtyard sitting on the layer one, and to use the courtyard plus appropriate stairs and walkways as the traffic ways to get to the laboratories on level 2 and the public spaces and offices on level 3. And it all worked out very well, and it turned out, and I'm not going to give you the whole miserable saga, but it all turned out in the end very well, and we got our building for the money we had, which is not usual.
Is there a particular individual who influenced this design?
That is a leading question.
Very much so.
Well, we'd sort of given the general verbal prescription to the architect that we finally took on, who was a very good architect, and whatever I say now is not intended in any way as critical of this architect. But at any rate, he served up various alternative ways of meeting these requirements. None of them seemed to us to be particularly good, but I was unfortunately in a situation where we had to meet deadlines, and I had to go with a final reaction to the designs, the preliminary design plans that were floating around in Sydney, and I had to get the first plane to Sydney. And I and my dear wife, in the early hours of the morning, agonised over these not optimal designs that were around, and my dear wife sat up in bed and drew what became the ultimate layout of the Pi laboratory in broad sweep. Not saying every detail was finalised at that point. However, structure. So I took this with me to Sydney and said, look, I believe we've solved the problems better this way than any of this stuff does. And the architect looked a little sad, but anyway, he took this on board. And the next thing he produced was, of course, the design that my dear wife Frances had produced, but regrettably we have no physical evidence of this because he was prudent enough to destroy it.
Fair enough, or unfair enough, depending on your perspective. One comment as a visitor to the Pi Lab, where everybody is greeted graciously, is it is clear that all the folks there have to say hi to each other, just bumping into each other in the process of the day, which is something that is missed in the establishment of many, many working environments. So in any sense I could use, I think it's a superb lab, my personal bias on that.
Well, of course, it's quite a small lab, and that helps. It means that it's really not much more than domestic scale rather than the inhumane scale of many places. And of course, once you get onto a larger scale, you can't avoid the sort of soulless corridor.
Right, but how many people work in there? How many people does it house?
Well, at this stage one, I guess we probably went up to about 36 or so, and now, of course, we've had, as you've seen, a stage 2 addition of 60%, which brings us up to a kind of capacity of, I don't know, 55 or so before we're too uncomfortable.
But that's the same thing. A large university department could function in a similar sort of space and do a much better job than they do now. That's something. Anyhow, I vote high praise for the labs there. John, we've chatted about some major components of work, but do you want to follow through at this point and say something about the 5 or 6 really main directions that have occupied you since you first started out in that research assistantship position?
Well, we've talked about 3 of them, I guess, and as leading on from Deniliquin. I don't know whether I need to say a lot about this, but one thing that I have been a little bit fond of is what I have tended to call the quasi-linear analysis. And this amounts to a little trick which allows you to linearize the steady unsaturated flow equation once you are prepared to accept a representation of the conductivity as an exponential function of the moisture potential. The first person who really recognised this possibility was Wilfred Gardner, but he didn't seem to, he had so many other good things to do that he didn't ever do much of a follow-up on that. And I was able to see, I was attracted, I'm a very lazy person, I was attracted by the fact that this quasi-linear analysis allowed us to get a whole budget of relevant solutions with relatively little effort, and that's the name of the game, in my opinion. And the great virtue of the quasi-linear analysis is that it really emerges in 2- and 3-dimensional problems. So it's really something that quite often is more useful in, if you like, man-made local geometrical complications than just simply in 1-dimensional situations.
Right.
It also is very useful in looking at these problems in arid regions when you don't have water tables within small distance of the surface as you do in many humid regions. And you see, well, I think I better not go down that track, it gets too technical.
Right.
But I just make the point that it is a wonderfully economical way of doing many things that are needed to be done, particularly in arid zone hydrology. One thing that I have also taken some pleasure in, although I don't believe it has been really put to too much use by the world at large, is the scattering analogue. And that is quite an interesting story, but again, I think maybe time is...
I think it's worth mentioning that.
Okay, well, I've done some work on quasi-linear solutions of steady infiltration from spherical and cylindrical cavities. And I was able to get the exact solutions as really series that involve Bessel functions. And this was all very well, except that there was a parameter coming into the solutions which was really proportional to a characteristic length of the cavity. And as this parameter became large, it became more and more difficult to sum this series of Bessel functions. And however, I did some rather busy numerical work on this, and a good friend who's a New Zealander mathematician in Canberra did much more. And we found to our surprise that for large values of this parameter, the the solution for the steady flow from such a cavity was equal to a certain quantity proportional to the plan area of the cavity multiplied by 1 plus a factor, and we call this parameter S, this parameter I was talking about, plus S to the power minus 2/3. And this seemed very strange. And I had no understanding whatsoever of why we got this magical power of S to the minus 2/3. But I happened to be in Melbourne in, I guess, about September '83, and I was giving this lecture actually to a group who were nominally meteorologists, but I knew there were quite a few mathematicians there. So I posed to the mathematicians there the problem of this asymptotics for large S. And at the end of the lecture, a shy figure came up and told me that he felt my problem was rather like one he'd treated in his PhD on magnetohydrodynamics at Cambridge in the late 1960s, which was what, I don't know, probably 15 years before. And he was Trevor Vector, and I had very interested conversations with him over the next few days. And it emerged that there was an exact and potentially fruitful analogue between multi-dimensional quasi-linear steady infiltration and the scattering of plane pulses and the harmonic waves. And, of course, there is a vast literature, an absolutely vast literature of scattering theory, which immediately becomes available for the solution of quasi-linear flow equations in hydrology.
Right.
And I think of that as a beautiful example of, if you like, the unity of science, the unity of physics, and how, what a shame it is that people get themselves caught up in, if you like, watertight compartments.
So there was a case, it was true serendipity. You could have hit a group of mathematicians and not had somebody there. But
well, if Trevor Vector hadn't have been there, they wouldn't have had a clue.
No, exactly. But that one opportunity, that one person could come forth, and you're able to spot it immediately, which is the key part.
Well, I guess so.
Yeah, that's important.
The other area of work that I would like to, perhaps to the point of boredom, say a word or two, is on swelling soils. And this is work that was done mainly about 69, 70. And I'm a little bit sad that it hasn't really seemed to catch on, and people haven't really grasped what's involved, I think, very much. And that is that there is a major difference between the hydrodynamics of swelling and of non-swelling soils. And let me do some acknowledgements. In this work, I owe David Smiles, who was a younger colleague of mine who was for some years chief of the Division of Soils of CSIRO, but before that was in environmental mechanics for many years. But I owed him a great debt in that he first drew my attention to the problem. And he was really one of the very early people to recognise that for unsteady problems in swelling soils, it is much more efficient to do the analysis in terms of material coordinates. It just cuts through all the dreadful complications. And I also owe Jerry Bolt from the Department of Soils of the Agricultural University of Wageningen a debt in that he made exact my initial rather rough and ready thermodynamic calculations of the overburden potential in 3-component swelling systems. So both those people really contributed importantly to my doing this work in a sensible way. But the real message of this work is that the fact of swelling completely changes the role of gravity. For a mineral soil, under normal swelling conditions, and normal swelling simply means that if you add a milliliter of water to a body of soil, that body of soil will increase in volume by 1 milliliter. Well, under those circumstances, the effective gravity is essentially equal in magnitude but opposite in sign to what it is in a non-swelling soil. So this means, for example, that the overall dynamics of infiltration in a swelling soil is more like the overall dynamics of capillary rise in a non-swelling one, and vice versa. But I don't want to sermonise about that forever. But it's, I think, worth making the further remark that failure to recognise the fact of overburden potential can lead people, and has led people, to think that some clay soil or other is virtually impermeable, when in fact nothing is happening because there's no potential gradient. There's no gradient of total potential, because they have not taken overburden potential into their calculations.
I think anyone watching this interview might just go back and restudy that problem.
Well, there's plenty of scope for them to.
Okay, okay. Any other areas in particular?
No, I think I've been pompous and boring enough.
No. What about nonlinear convection, diffusion,
well,
inverse similarity?
Oh, okay. Well, I suppose I've always been, I've always had nagging at the back of my mind the possibility of using various nasty mean tricks to get solutions of nonlinear diffusion and nonlinear convection diffusion equations. And I've been a little bit lucky in sometimes seeing how one can get exact solutions through a similarity trick, and also in that one can quite often produce, or not quite often, but now and then, produce, if you like, an anthology of exact solutions simply by using an inverse trick, saying, okay, well, if the answer looks like this, what did the diffusivities and the convection velocities look like?
Right, to give you that answer.
Yeah. And, well, that's a childishly obvious thing, but nobody seemed to have got round to it until the sneaky
we just need a mischievous older child to have a crack at the problem, right?
Well, could be.
Could be something like that.
Could be.
John, one thing that comes through from all the areas of work, you've always had quite a few strands of research going in at a given time. So if you hit a roadblock at any stage in any of them, you have the opportunity to roll across to some other one and keep going. Would you offer that as a piece of advice to particularly younger colleagues starting out?
Well, yes, except I wouldn't say that I've ever done that consciously. I mean, unless I'm losing my mind and losing my memory, I have always at the back of my mind the totality of the work that I've been involved in, the totality of the problems I've worked on. And I'm also aware that there's always scope for improving the solutions to problems. So everything is provisional in science in a certain sense. And so I hope that, you know, it's really the prepared, it sounds pompous, but the prepared mind can opportunistically sort of dive into something, provided there's all the background there, quite beside the background there. But that doesn't mean that you consciously say, ooh, I must have a shopping list of 5 things in case I get mucked up on this one.
Right. But the key bit is there's a certain time and a conditioning to recognize particular things. Can you think of any examples of work that you've done that if you'd bumped into them maybe 15 or 20 years sooner, you may not have recognized some of the pieces that made it possible for something to come together?
Well, I think maybe I've got a current example of that, in that the work that I'm doing on blending levels, remember I mentioned that I'd been able to build on some early work on local advection recently. Well, it so happens that it wouldn't have clicked in my brain that I could do this work if it hadn't been for 2 quite disparate things that that I'd done over perhaps the last, well, actually it's a while now, over the last 25 years, namely around 1970. In a totally different context, I had done some work which was untangling the existing confusion in the phase functions of the Kelvin functions.
Right.
which we don't have to go into details of what that is, I hope, and you hope. But the other thing was that 2 or 3 years ago I was working in a laboratory of CNRS in Poitiers in France, and I was called on to do what was really a straight exercise in chemical engineering, which involved really looking at the convection diffusion problem of deposition on the walls of a channel of a Brownian suspension. Well, I attacked that problem by converting it into a convection diffusion problem with a convective velocity, which was a power law of transverse coordinate. And suddenly it sort of dawned on me that I would have the same class of problem in looking at the problems of the solution of the atmospheric convection diffusion equation with power law descriptors of the velocity profile and of the eddy diffusivity profile, to look at the blending problem with arbitrary periodic boundary conditions at the Earth's surface. And the fact of periodicity led immediately to the Kelvin functions, and fortunately I knew my way around the Kelvin functions well enough to be able to proceed in a reasonably lazy and painless way.
This laziness you referred to on several occasions, John, I don't know too many people who get up at 4:30 in the morning to do serious science and get the best part of a day's work done before other people get to the office. So I'll have on the record that you're not lazy, and you couldn't possibly be. You might choose to do things that are less painful to you than others, but you don't fit the category of lazy.
Well, I don't do much for the rest of the day.
Well, some people get a lot of work done in a few hours, or whatever it would take care of there. When we were chatting some time ago, before this interview, we were discussing some issues on heterogeneity and how this seems to have some folks a little bit troubled and so forth and so on. And you mentioned you were putting together a current article for an encyclopedic piece of information on hydrology. And why don't you read the thoughts that you had on that? Because I think that's important for people to think about. And then I want to pick up on that and follow on from something you wrote in 1975. So,
well, I think it's very boring for people to
no, it's not. Just
talking. It's bad enough to have a talking head, but a talking head reading.
Well, you read it to me.
That must be the stone end. But anyway, what I do say here is this. Often soils change in properties with depth, either gradually or in layers. These modes of heterogeneity on the local scale are more important for unsaturated flow processes, and this article is about unsaturated flow, than is the larger scale horizontal heterogeneity that may arise in the saturated flow problems of regional groundwater hydrology. Provided the spatial variation is known, soil water processes in these systems may be analysed through extensions of the approaches of, in fact I say sections 2 and 3, but that was really talking primarily about problems in uniform soils. Important elements not present in analogous homogeneous situations may arise, such as unstable flows, perched water tables, and hysteretic behaviours. Complications may be produced also by micropores and cracks. When their disposition is known, their influence may be estimated using models of aggregated or cracked soils. Ian White, a colleague of mine, I add parenthetically, has observed the useful simplification that even when macropore variability produces large heterogeneities in saturated permeability, such macropores are empty of water at small negative values of the moisture potential, so that the heterogeneity may have little effect on the hydraulics of the unsaturated soil. And then I go on to say, obstacles to analysing soil water behaviour in unsaturated field soils arise in two ways. First, the magnitude of the task of measuring adequately the spatial variation of hydraulic properties, and secondly, the magnitude of the task of performing the consequently elaborate calculations, even if a proper specification of properties were to hand. And then we go on to say, many workers have pursued stochastic methods of evading these problems, or hopefully evading these problems might be more realistic. The logical difficulty of stochastic approaches is that they depend on assumptions of stationarity and ergodicity. Stationarity can seldom be verified, and ergodicity, excuse me, I have to dismantle this. Ergodicity demands an unbounded ensemble of realizations, where there is not even a finite ensemble, simply one reality. And then I shiftily arrive at the following conclusion. Clearly, there are deep methodological difficulties, and it may be that some questions put to saltwater hydrologists will be recognised ultimately as trans-scientific in the sense of Alvin Weinberg. Although they may be posed as scientific questions, precise answers lie beyond the practical power of natural science.
So here we are in 1995, and you're reminding people of that. And I think you were the first person to bring to the hydrologic community the concept of trans-scientific. And this happens to be in a publication, Prediction in Catchment Hydrology, edited by Tom Chapman and Frank Dunnan. And in this particular case, you talked about science and catchment prediction. On page 29 of this, you said at the end, "What, you may ask, is the point of scientific hydrology if the problems it seeks to solve are ultimately trans-scientific? In my opinion, the answer is that it remains our obligation to ensure that our methods are as scientific and objective as possible. Let us at least work towards a situation where the trans-scientific judgments which practical hydrologists are forced to make are informed and sustained by a truly scientific hydrology, a skeptical science with a coherent intellectual content firmly based on the real phenomena. Finally, let me repeat the text of my sermon. The most science can do is to inject some intellectual discipline into the Republic of Trans-Science." So we've come...
Good stuff.
Good stuff. Okay, John, I think that's an important part to have in there. There are some other dimensions of you as a person, a scientist, an administrator. We've been talking about the activities of the Pi Lab. Through your activities there, you built up a group. It became the Division of Environmental Mechanics. And I think it's clearly the complete spectrum to me of what environmental fluid mechanics could be, including biology, the many, many elements in there. And during that time, you took on a stint as a division director in CSIRO, and CSIRO had something on the order of 7,000 people at its peak.
Institute director was the jargon.
Oh, well, the jargon I'm likely to get wrong, John,
Sure.
but CSIRO had on the order of 7,000 or 8,000 people, on the order of 5,000 of whom were research scientists, if I remember correctly. Now, the group that you had in there at the biggest stage in environmental mechanics while you were heading it was on the order of about 40 people.
Right.
So there was a group that was one of the most productive, and now it's called the Center for Environmental Mechanics. And as a scientific entity for productivity, there are very few outfits that would even match it. But there are some things that are negative about CSIRO in that it's a group of scientists, it's a countrywide organization. In many ways, it's like the research arms of many of the non-military government labs, say in the United States, all in one place under one administration to try and get work done. One of the things you tried to do was to get greater involvement with graduate students so that it wouldn't be a monolithic group of people all getting old together, bringing in a few young ones.
Sure.
If you're able to build a CSIRO, how would you structure it now? Yeah, we'll make this short because I know this could take 5 hours. But if you were to do that, how would you try and do that? And the importance of having students of different level of activity.
Well, of course, I would, as I have been saying to the point of boredom and irritation of many of my colleagues for many years, CSIRO has lost a great opportunity by not working towards being, if you like, a continent-wide institute of technology which in fact receives graduate students and produces graduated students, if
Right.
you like. And the rationale for this, of course, is that there are many scientific expertises in CSIRO that do not reside in the universities. Furthermore, there is nothing in the universities which really gives any serious bias towards national interest in the lines of work that are followed out. Now, I'm not someone who wants to put research in railroad tracks, but the point is that in many cases, something which is of national interest is equally possible as something which is some ivory tower academic's hobby.
Right.
The other point is, of course, as you remarked, that CSIRO is an ageing organisation, and it would be wonderful to have machinery in which the young came in and kept the old codgers on their toes and, one hopes, honest now and then. And that would be terrific. And, of course, there's also the brutal fact of having a few more pairs of hands around. Well,
Might get a few things done.
something like that. But, of course, this suggestion is absolute anathema to the universities, who've really still got a hangover of the resentment from the times when CSIRO was really the only research body in the country. And I don't think the universities were ever going to look kindly on something which seems to tread on their preserves.
But it's still something, the links need to be established or
Of
strengthened.
course,
There
I
are
mean,
some.
There are some links, and there are all sorts of ad hoc arrangements in which we've had not as many as we'd like, PhDs in our lab. But this depends on, if you like, a kind of person-to-person arrangement within, for example, the National University, in which someone in our lab is simpatico with someone in the university, and they end up with a joint supervising arrangement. But that, unfortunately, doesn't happen as often as one would like, and there's nothing in the way of a formal arrangement.
Right. I mentioned a little on the administration part there. By any measure, you've taken more than your share of administrative activity, but you've mentioned on several occasions, in a retirement speech, in several honours acceptance speeches, how you managed to function in that setting and how it was possible to get research done and do administration, and any suggestions for people who are caught in that mode.
Well, I think you have to be both lazy and selfish. And
we need to follow up on that.
Well, do we? Well, and the point is that my laziness and selfishness has largely involved being, and good luck, I guess, also. I've been very fortunate for many years when I did have my more intense administrative loads of having as my personal assistant Dr. Philip Ford, who has been someone who has really somehow been able to plug in, if you like, to my particular set of violent prejudices or beliefs or whatever. And I've been able to do a marvellous job of delegating many things to a man who's been a real saint, as far as I'm concerned, and has over the years taken off my shoulders burdens that I should have been carried and that he's carried.
So collectively between you could run the place and
Well,
still
you
get
see,
your research
he
done.
has such a splendid grasp of the research ethos. He has probably a much wider overall understanding of the total texture of science that goes on than I do. And he's a genuine intellectual, and I've found it absolutely marvellous working with him.
He was someone you hired in the first place?
Yes. Luck again, of course.
Luck again, John. What can we say? In many ways, the way you're able to function while doing administration and research is not atypical, is not too terribly different from the way Sir Peter Medawar managed to function while he was doing the bulk of his research in England. So maybe there's something in parallel here, only different fields.
Well, who can say?
You're not going to bite on that, okay. Given what you're able to do with enormous scientific productivity while you were doing administrative things as well, is it possible today, or do you think we've got ourselves into a structure that's not very healthy for doing those two things?
This sounds like a leading question.
It is a leading question.
I would have to say that I cannot see any way that anybody starting out today could live on their luck, as I have done, and to be in systems which had the flexibility, the non-rigidity, to be able to tolerate the kinds of ways that I have been bloody-minded enough to operate.
Right. You don't want to take that any further?
Well, there's nothing more to say. I just don't think, I think that I'm terribly fortunate to have existed 50 years before now rather than now.
The game has changed considerably.
Well, it's no longer a game.
Right.
It's just a beastly business.
But this ought not to discourage young people from having a crack at things.
Well, I don't want to discourage people, but I think that really the sad thing is that, in my view, the young of today meekly accept an absolutely intolerable regime of scientific management, and they just think it's the way the world is. But I know I'm sounding like a very old man when I say it is not the way the world was, and it's not the way the world has to be.
That's not the way it could or should be either.
Yeah, well, that's my view, but then again, I'm just an old codger.
I would hope that many people who get to be an old codger of your age still have the same energy and effort and capability to chuff ahead and turn out results, John, but that's okay. There are other things. We've been chatting largely about scientific activity, things within CSIRO, which the bulk of your scientific life has been there. And we could also talk about life across science, sport. Very few people know some of your interest in sport. We've alluded a little bit to architecture. We could talk about the arts. We could talk about history. And few know that until about a decade ago that you were a fanatical cricket player. And I'm told that people, I hear this secondhand, that those who had to face your bowling were rather nervous on occasion. And it's also known that you were still able to do a pretty commendable job with a ball in that game some time ago. That may be appreciated by people who know the fine points of that game, but let it be known that you at least did other things than get up at 4:30 in the morning and do science.
Well, okay.
Fair enough and
I'll
all that.
settle for that.
A few other things that folks may not have seen. Your interests, I think, would be eclectic, Catholic, in many, many ways. And one that comes to mind that I think of is an incisive review that you wrote of the book by Paul Davies, The Mind of God. Mm-hmm. Very few people would have seen that. It was written and published in Overland in 1993, and I think they ought to go and dig out a copy of that because it shows how a very sharp mind can look at the arguments of somebody that many other reviewers got excited about and didn't see the fallacy in the fundamental argument. So there's a case where you go completely into different fields and can nail someone to the floor. I'm sure the person is still selling lots of books and has not been fully nailed there. To architecture, your house is one of the most amazing houses anyone would ever see. I think unique is the fair and true description. The Pi Lab, if it hadn't been for your interest and Francis' interest in getting something that's really functional, I don't think it could have been quite as productive a scientific home for many, many people. So there's something very special in that part there. There's a sense of your history and a worrying about historical activity. And I remember a marvelous seminar you gave on our campus entitled Desperately Seeking Darcy in Dijon, now published by the Soil Science Society of America. Would you just say a few things about that of somebody who was absolutely famous at the time of his being around and revered, and how he's even seen or otherwise today?
Well, I don't know. I can't go on at any length about this. The basic story was that I went to Dijon in the expectation that I would encounter some of the, if you like, the relics of the great Darcy, who in his time was so esteemed in Dijon that the main square is called after him, as well as everything from a Renault garage to a pharmacy to a cinema, etc., etc., etc. And when I asked at the Tourist Bureau about all this, no one had ever heard of Darcy. It was simply a geographical name like Piccadilly or the Loop.
Right. So all the people who work on Darcy's theory and just assume that everybody knows about Darcy, if they were to go to Dijon, they'd find out that A, he was famous at the time, was a hero of the town, and today people wonder who the hell he was.
That's right. So,
Is there a message here for people?
well, dear children, fame is ephemeral.
Right, something about that. There's something else that few people would know about you, John, is over the years you've been interested in writing poetry, amongst other things, and you find it an efficient form. And I'd like, if you would be gracious enough to do it, you've been more than gracious already for this interview, if you'd maybe share a couple, because I think in a few short ones that I looked at with you yesterday, it says a lot about how you view things, and in your prose, I think you have a way of saying something to people and getting them to sharpen their thinking. So would you like to? You probably wouldn't like to, but I'd like you to.
I think our moderator is looking very impatiently at his watch.
Well, I've been watching a clock too, and we're within our time, so
Okay,
we're in
all
great
right.
shape.
Well, I mean, I hate to be boring about this, but
Please.
you know, at your behest, I have brought some of my music, but I'm not sure what you want.
I think you might read Cat and Dog to us.
Okay, all right. Will do. Cat and Dog. A poem is like a cat, coiled to spring, economical in action, views the poet coolly, cleans itself, grants an infrequent small purr, concedes little else. But bad verse, dog-like, adores its author, reinforces self-reverence, dog breath and clumsy congratulation bounce on both interminably.
Now, you have in that pile two more. How about sharing one with us?
Well, as we rough Australians say, you're a tiger for punishment. Well, this thing is called Theorems and Metaphors. With all said and done, theorems are tautologies, unobvious and wonderful perhaps, but merely jewelled elaborations of the known and trite. Such, alas, are time and light, that theorems cease to stand alone and sink in the swamps of trite and known. Theorems enlarge, but metaphors connect. Analogy is not tautology, but deepens meaning multiply. Better enrich the web of words than find a property of surds, though time tarnishes metaphors too, so poets must restock the zoo.
Thanks, John. Just to bring to our to completion our interview, there's something that I'd like to read for this interview. Back in February 26, 1992, was nominally your formal retirement. Now, if I remember rightly, next January is your 69th birthday.
Mm-hmm.
I'm not sort of doing that to remind you of something, but I hope I can be pushing half as well as you are by the time I ever make it to that part. But there's something just near the end. You said the following: "But I will say that in my lucky life, my greatest piece of luck is to have fallen in love with someone of such keen intelligence, lively wit, independence of spirit, and downright courage as my wife Frances. I cannot imagine anyone who could have helped me so much or kept me on the rails so well."
How true.